Hello, so in this video we're going to be doing some revision about AQA mechanics and materials. It's actually quite a big topic, so I'm going to have to leave the materials to another page. Now, because it's so big, there are timestamps on YouTube beneath this video, so you can skip forward to the bit you need. Again, talking of YouTube, don't forget that you can subscribe to me at Physics Online and also look at my website to find hundreds more videos. It's definitely worth having a look at. Anyway, let's start with the first part of mechanics, which is looking at quantities. Now, there are two main classifications. We have scalar quantities and we have vectors. And as you'll recall, when we have something which is scalar, it only has a size, or in A-level we call this a magnitude. Whereas if you've got a vector, the direction is important as well. And what we do with vectors is we represent them with arrows, where the size of the arrow represents the magnitude, and then the direction of the arrow represents the direction of that vector. We're going to do a lot more about vectors in this video. So common examples of scalars include distance, speed and mass, whereas when we have vectors we have things like displacement, velocity, acceleration, weight and force. And we're going to talk a lot more about these in the video. So the displacement, rather than being the total distance that something's travelled, maybe going from a point to a point, this might be how far the object's actually travelled, but the displacement is how far it is from the start position and at which angle it is. Velocity is the rate of change of displacement, acceleration is the rate of change of velocity. Hold on, that's not mass, that should be weight. Weight and mass are often confused in everyday life. Mass is just a property that objects have, whereas the weight is the force exerted by gravity on those objects with mass. So let's think in a little bit more detail, about vectors. Because what we can do with vectors is we can add them together. Maybe we have perhaps a vector of displacement, and we add that to another vector of displacement for different parts of its journey. What we can then do is find the result of these two things. Maybe sometimes the vectors that we're adding together are at angles other than 90 degrees. And what we can do then to find the resultant is we can use scale drawing. Now, this seems like quite a basic skill, but it's something that people find quite difficult. Basically, don't forget to use a pencil and a ruler and also your protractor. And what you can then do is you can draw your arrows proportional to the size of the vector, measure the angle with your protractor, and then find the resultant of these two things added together. But actually, I'm a bit more interested in what happens when you have vectors at right angles. Now, it could be that we're adding displacement vectors together. It might be that we have some of the objects acting on an object, and we maybe have a free body diagram where maybe there's a force in this direction, there's another force at 90 degrees, and we can then find the resultant of these two things here. And what we can then do is we can think about our calculations. Now, you're going to be doing a lot of this in the maths classroom, but this is just a reminder that there are two main things you need to know about. So with a right angle triangle, which is the kind of thing which is it comes up all the time across all bits of A-level physics, is if you want to maybe find the side of a third length of a right angle triangle, so you've got this side is A, that's B and that's C, from Pythagoras we can say that A squared is equal to B squared plus C squared. This comes up all the time. It's a really quick and easy way to work out the magnitude of the addition of a couple of vectors. So don't forget about Pythagoras. But something else we can do, and this is actually probably even more useful, is we can think about trigonometry. And again, for a right angled triangle, perhaps we know one of the angles. Then if this is the angle theta, we can start to identify the three sides. The longest side is always a hypotenuse. The side opposite the angle is our opposite side, and the side next to it is the adjacent. And there's basically a relationship between the ratio of these different sides. What we find is that if you look at the ratio between the opposite and the hypotenuse, there's a relationship to the angle theta where we say that sine theta equals opposite over hypotenuse. When we look at the adjacent and hypotenuse, we have cos. Opposite and adjacent is tan. The way I remember this is SOHCAHTOA. And this means that if you know two sides, you can work out the angle, or if you knew one side and the angle, you could work out the other side. This crops up all the time. You'll have seen it maybe at GCSE, you'll be doing it in A-level mathematics, and it will come up all the time across every single module. So these are kind of really important skills to get used to. So what we can do is we can maybe start to add vectors together, or maybe we look at the result of different force vectors and their resultant force. But something we can do is also look at resolving a vector, so one vector, into its two components. Now what I'm going to do is imagine that we have a force, F, acting at an angle, and the angle is maybe to the horizontal theta. Okay, so this is our angle, that's the size of it. What we can do with this force is we can resolve it into effectively how much of the force is in this direction and how much of the force at 90 degrees is in this direction. So if I just put this, I'm going to call that Fy to be the force in the y direction, and along the bottom we've got the effective force in the x direction. Now we could call this horizontal and vertical. I'm just going to use x and y for this one here. Now there's no triangle drawn here, but we can start to sort of see and imagine that there is actually a triangle, and if I just put in that side over here, the length of this side is equal to Fy, the length of that is Fx, and that hypotenuse is F. Now on this one here, I'm just going to label the longest side, which is F, as H, to be the hypotenuse. If we know this angle theta, that's the opposite side, and that's the adjacent. Now suppose we wanted to calculate the size of the horizontal component of force if we know the force and know the angle. Well, if we know the hypotenuse and we know theta, we're trying to find the adjacent side here. So we're going to be using cos. So what we could say then is that in this case cos theta is equal to our adjacent side, fx, divided by the hypotenuse, which is f. Now we want to find this, we can then say that fx is equal to f cos theta. If we wanted to find the vertical component, we'd go in a similar manner, but this time we're looking at effectively the opposite side in the hypotenuse, so that's sine. So Fy is equal to f sine theta. Okay, so what we're doing here is we're resolving this vector or splitting this vector up into its horizontal and vertical components. Now we can do this with things like velocity. It happens a lot with forces, and sometimes this is a really good thing to do if you maybe got something on the table, there's forces acting up and down and side to side. But again, at A level, we start to sort of tilt things around. And a really common example that you might be asked about is an object which is on a slope. So this thing here is my slope at an angle of theta to the ground. I'm just going to draw it as a dot, because this could be any object, but this dot is what we call a free body diagram. And this is where you draw the forces acting on one object. Now, there might be a force down due to the weight of that object. I'm going to call that W. There's going to be a force at 90 degrees to the surface, and this is our normal contact force. This is the support force of that slope acting on the object. And maybe we've got a situation where the object is in equilibrium. We're going to come back to this again, but effectively what we can say is that if this object is in equilibrium, then there's going to be no resultant force acting on it. So that's our normal there. I'm just going to put F to be my frictional force. Now, what we can do in this case is rather than resolving all of these forces horizontally and vertically, effectively we can maybe think about our axis being in line with that plane. So you might be thinking about the forces in line with the slope and also the forces at 90 degrees to the slope. So we've got to imagine that we turn everything around. And what we could then do is we could maybe look at the component of weight which is acting down the slope, down here, and there's going to be a component of weight acting at 90 degrees to the slope as well. Now if this angle is theta, this angle in here is going to be 90 minus theta, and this angle in here is going to be theta. So what we could now do is we could then resolve our weight into its two components. Now, provided this object is in equilibrium, so it could be stationary or it could be sliding down at a constant velocity, let's first of all look along the slope. Now, along the slope, we can say that maybe the force, the friction acting up is equal and opposite in size to the component of weight acting down. So there's going to be a component of weight, and if it's this angle over here, that would be sine theta. Now, if we think about 90 degrees to the slope, then in this direction we've got the normal contact force, and there's a component of weight acting at 90 degrees to that surface, which is going to be W cos theta. So what we've done now is we can basically split up our weight into its components along the slope and at 90 degrees to the slope, and if it's in equilibrium, we could then equate these to the frictional force or the normal contact force. That's a really common example, but I've seen loads of different exam questions, and this is the whole thing. Although I'm talking about some of the mathematics and some of the pure physics, you've got to spend the time having a look at lots and lots of past paper questions, lots of worked examples, to see all the kind of scenarios that they could come up with where they might test you on this. But effectively what we've got here is different ways in which we can resolve vectors on a slope, or resolve vectors into their horizontal and vertical components. So here I've done it very much with a free body diagram. I've drawn arrows and I've done some calculation. But I said here about scale drawing as well. Now, the other thing we can see about these arrows here is if you added maybe, in this case, this is the size and direction of that normal contact force. If you then added on another force strip, perhaps the friction force, and what we're doing is we're just adding the vectors end to end, then the weight would be this final side of a closed triangle. Effectively, N plus F plus W equals 0. And if you add the forces together and they make a closed triangle, that means there's going to be no resultant force, and therefore the object is in equilibrium. Okay, so we've talked about equilibrium, and basically there are two conditions for an object, which could be anything being equilibrium. Now the first one is that the sum of the forces on that object is equal to 0. So the forces up equal the forces down, the forces left equal the forces right, so there's no resultant force in it. The other thing, and this kind of symbol here, this kind of crazy sideways M, this just stands for the sum of. The other thing is that the sum of the moments on that object is also equal to 0, and that means it's not going to be turning or rotating. So let's have a look at moments over here. So a moment of a force is if you have a force acting on something at a distance from a point. Now it doesn't have to be a pivot that's going to be rotating, we're just thinking about a certain point over here. And I was going to put this distance as d to stand for the distance from that point. What we can actually say is that the moment is equal to the force times the perpendicular distance from the point to the line of action of the force. Okay, a bit of a mouthful. And this is important. So say for example we had maybe this is a point over here. We've got a distance which is x. That's supposed to be a straight line. But now the force is acting at an angle. So rather than being kind of perpendicular like this, it's kind of acting at an angle. What we want to think about is if we're to follow the line of action of that force back again, it's the perpendicular distance in here that we're interested in. Okay, so not the total distance to the point where the force is acting, but it's the distance to the line of action of that force. So say for example, this was acting at an angle of theta in here, then the size of this distance here would be equal to x cos theta. So to work out the moment here, again it would be the size of the force, in this case times x cos theta, which is our perpendicular distance. So that's moments, and we also have another kind of special case, which is where we have a moment of a couple of forces. And a moment of a couple is if you have something where there's maybe a force acting down and a force acting upwards, and these forces are perpendicular, so the forces are parallel to one another, but they're a distance apart. If we were to think about the sum of the forces acting on this object, well, the size of the force up equals the force down, but there's still a turning effect. And the turning effect is equal to the one of the forces times the distance between them. So I'm just going to put the distance between them as capital D to show it's not the small d we had up there. And it doesn't matter about where you take moments from. So if we took moments about this point over here, the total moment would be equal to F times D going anti-clockwise. If we took the moment about this point, the total moment would be equal to force times distance, again anti-clockwise. If we took it from the middle, it would be a half FD plus a half FD, both anti-clockwise. So in this case here, the moment of that couple would always be equal to the force times the perpendicular distance between them. It's very much a special case. Now the other thing with moments is that we can think about something called the principle of moments. And the principle of moments basically says that if you've got a system which is in equilibrium, then the total clockwise moments are equal to the anti-clockwise moments. Effectively, the sum of all the moments on that system are equal to 0. And there are lots and lots of things which are balanced, and therefore this is really useful for many sorts of problems. The other thing we can think about is, in terms of stability, is the centre of mass. And effectively this is the point at which the mass of an object appears to act. For simple things like a triangle, it's in the very middle of the triangle. For a square, it's in the middle. For a circle, it's in the middle. Effectively, for these uniform shapes, the centre of mass always acts at the centre. And again, if this is where the centre of mass is, that means this is also where the centre of gravity, or where that weight force, is acting. And provided that this centre of mass is within the base, you've got something which is quite stable. But this is something to consider. So we're not just thinking about our normal basic shapes. We might be thinking about a ruler where we've got different masses hung on it. Again, the centre of mass of that ruler is going to be in the very centre midpoint over here. So again, this is some of the basic physics, but there's loads and loads of examples where this crops up. So it's worth having a go at as many questions as possible. So now let's have a look at the motion of objects in one dimension. So let's just have a bit of revision, hopefully. If we want to look at the speed or the velocity of an object, that's equal to how quickly its distance or displacement is changing. So we can say that v equals delta s over delta t, remembering of course that we use s for displacement. And there are really two sorts of things we're interested in. We're sometimes interested in the average velocity, for example, and this is going to depend on the total displacement over the total time. But sometimes we also think about the instantaneous, and that's very much what that value is at a particular time. The other thing we can think about is not just the rate of change of displacement, but also the rate of change of velocity, and that's what we then call our acceleration. So these are equations that you might have seen before, but we're going to come back to those in a little bit in a few minutes' time when we look at suvat equations. But equations are all very nice, but actually sometimes it's quite nice to look at motion graphs, and this really kind of brings stuff to life and makes it a lot easier to understand. Now there are three, maybe five main types of motion graphs. The first one is maybe one where we look at displacement and how that varies with time. GCSE, we might just have done a distance time graph, but now we're looking at displacement. And for that reason, we might look at the motion of an object, how over time it might do something like this, where the gradient basically tells us the rate of change of that displacement. Now, if it's displacement, it can have a positive value and a negative. If this was a distance time graph, then the distance would always be increasing. There'd always be this positive kind of trend to that data. Now, the gradient here, m, is going to be equal to our change in s value divided by our change in time. And that means, as we've seen up here, the gradient is then equal to the velocity. So you might have a uniform velocity here. We then have zero velocity because it's stationary, maybe an increased velocity and then a negative value of velocity. So that's what we get from a displacement time graph. Thinking about velocity, of course, we can also think about a velocity time graph. And actually it's often really useful to think about both positive and negative values of velocity and looking at how these change with respect to time. And what you might find is you maybe have an increasing velocity, a constant velocity, and then maybe a decreasing velocity like this. Now, at this point over here, we have a constant gradient, and here that gradient, m, is going to be equal to our change in velocity with respect to time, and therefore that means the gradient is equal to the acceleration. And here we have a uniform or constant acceleration. We then have something here where there's no gradient. That doesn't mean the object stopped, it just means it's going at a constant velocity. And over this point over here we have a negative acceleration, which is often called a deceleration, but now we've got a curved line, and that means that this is non-uniform. A final graph that we can draw doesn't come up that often, but if we've got displacement and velocity, we can also have acceleration. Again, we can have positive and negative values, and we can see how these vary with time. And it might be that you get a graph that looks a bit like this, perhaps. This one here would have something where there's a constant negative acceleration. And often when we're looking at projectile motion, we have to choose our direction for positive and negative. If we say upwards is positive, then on an object which is maybe being projected is always going to have a negative acceleration, which is constant, a bit like this. So these are just some of the graphs that you might see. So that's all really good. That actually allows us to maybe visualize what's going on. But what we really want to do with motion is maybe think about motion, first of all, in one dimension. So we might be thinking about motion along a straight line, or even the motion of an object that goes up and then comes back down again. So it's not just things horizontally. Now, let's look back at these equations over here. We've got an equation here that says v equals delta s over delta t. Now, if we wanted to look at the average velocity, this is going to be equal to the start and final velocities and their average value. So that's going to be our average velocity, where u is its initial value, v is the final, and that's going to be equal to its total displacement divided by time. Now, what we can do with this equation over here is we can rearrange this to say that s is equal to u plus v over 2 multiplied by t. Another equation we can do is say, well, okay, over here we say that a is equal to our change in velocity, which is v minus u over t. We can rearrange this equation to make v the subject, and therefore this equation here becomes v equals u plus at. So these are two equations that we've already seen, just written in a slightly different format. Two other equations that we've got include s equals ut plus a half at squared, and also v squared is equal to u squared plus 2as. And what you might see is that there's certain terms that come up all the time. What we have over here is we have an s term, a u term, a v, an a, and a t. Now this first one over here, we've got a v, u, a, and t, but we don't have an s. This one over here doesn't have an a. This one doesn't have a v. And this one doesn't have a t. And that's really useful, because that means if we know about the displacement, the initial, the final velocity, the acceleration, or the time, if we know any three of these 5 bits of data, 3 bits of data can be used to find the fourth, which could then be used to find the fifth. And depending on which data you know, that's when you select which equation to use. So these are called the suvat equations. And I would urge you, if you come to a problem, is what you need to do is, if it's about the motion of something, just write down, and I always do it vertically so I can actually fill in my data, write down the letters of suvat. What you can then do is start to fill in what you know. So maybe you've been given a distance, you can convert that distance to meters. Perhaps the question is after you working out the initial velocity, so maybe just put a question mark to show that's your unknown thing that you're going to try and find out. Perhaps your final velocity is in meters per second. You've been given an acceleration in meters per second squared, but your time hasn't been given. So now we know 3 bits of data, we know the 4th bit of data we want, and we know what we haven't been given. We can then check that out of these equations here, v squared equals u squared plus 2as could be the right one to use, because this doesn't have a t term in it. And we can then rearrange this to find out what we're trying to look for. So we can say that u is equal to the square root of v squared minus 2as. So when it comes to approaching problems involving motion, write down suvat, identify what you know in the correct units, identify what you don't know, select the appropriate suvat equation, and then rearrange. Now you can just plug your numbers in and the final answer just comes out. Easy. Well, it takes a little bit of practice, but you get the idea. So that's looking at motion in one dimension. But obviously this is A-level, we're not GCSE students anymore, so we can also think about motion in 2 dimensions. And what we're thinking about now is the motion of projectiles. Perhaps we've got maybe something like a bullet over here. And when you've got something like this, you might find that there's maybe a force in one direction, maybe this is due to its weight, but there aren't any other forces in the other direction, and that means that we can then kind of consider the independence of its vertical and horizontal motion. Now the 2 main examples, you've got things which are maybe projected initially horizontally, and then they have this parabolic path here. Or you might have objects which are projected at an angle from the ground, they go up and they come back down again in this parabola. Now when it comes to equations like this, again the bit of advice I'd say is just to write down suvat. And if you write down suvat and you do it 2 times, you can then start to fill in the bits of data that you know from whichever question. Now, the thing is here that this initial velocity is going to be equal to the final velocity, because in this case the acceleration horizontally is going to be 0, and this is because we're going to assume that there's no air resistance or water resistance or other kind of drag forces. In the vertical direction, well, it might be that you say, and it's up to you to decide which is the positive and negative direction for these vector quantities, we might say that upwards is our positive value. Now that means if upwards is positive, anything downwards must be negative, and often the acceleration downwards is going to be equal to g. Now g kind of stands for two things. So g is the acceleration due to gravity because of the gravitational field strength. Now the value for the acceleration due to gravity is equal to 9.81 meters per second squared, because the gravitational field strength on Earth is 9.81 newtons per kilogram. So a lot of the time when it comes to these problems, the acceleration that something might experience is due to g, this acceleration due to gravity, which is something that you will probably at some point have had a go at measuring in the lab. So with this one here, you kind of get your bits of data, and it might be that there's 10 possible bits of information you could have. Well, I suppose really 8, because we discount the acceleration. We know that u is equal to v. You fill it in over here. You can then start to work through using the appropriate suvat equation to find the bits of data that you need. And as you start to find out more, it might mean that you maybe look at the time of flight. And then because it's the same object, this time might feed in over here. Again, projectile motion is quite tricky, and it just takes you doing lots and lots of examples. But this is, of course, in our perfect ideal world where there's no drag. In reality, moving objects will experience some kind of drag force. Okay, so it might be that it's stopping it moving as fast. So maybe rather than following this parabolic path, in reality we might get the effects of friction causing it not to travel as far. But it might also be objects which are moving down vertically. Perhaps we have a ball which is dropped. As this ball, there's always going to be a downwards force due to its weight. As it gets quicker and quicker, the drag force is going to increase, because effectively the drag force depends upon the velocity of that thing. The quicker it's going, the bigger the drag force. And what happens then is it doesn't have this uniform acceleration that we've always assumed for these suvat equations. In fact, it gets to a terminal speed. And if we were to look at a graph of its motion over time, where we look at its velocity here, and this is the time, what we see is that it plateaus until it doesn't get any quicker. And the reason for that is due to the forces acting on the object. Initially, the only force acting is its weight acting down. As time goes on and it starts to accelerate, the drag force is going to increase. That means there's less resultant force, so the acceleration is smaller, until we get to this point over here, where the weight is equal, but in an opposite direction to the drag force. There's no resultant force, and therefore it keeps going at that same terminal speed. So this is just a little bit more about motion. And if we consider the effect of the forces on the motion of an object, what we can then think about are Newton's laws. Okay, so there are 3 Newton's laws that you should be familiar with. You should know the definitions. So let's just think about Newton's first, second, and third. Okay, written them all out. It's taken a while. So basically, Newton's first law says that if there's no resultant force on an object, it will remain at the same velocity. Now, this velocity could be 0. So stationary objects remain stationary. Things which are moving keep moving at that same velocity. Newton's second law, though, is about if there is a resultant force in this object, the size of that resultant force is proportional to the rate of change of momentum. So we can say that F is equal to delta mv over delta t. Provided we're using kilograms, meters per second and seconds, we can measure our force in newtons. We'll come back on to what we mean by momentum in a second. And the last one is about the force between 2 different objects. About if we've got object A and we've got object B, these both exert an equal and opposite force of the same type, so it could be electrostatic or gravitational, and just as much as A is affecting B, B is affecting A by an equal and opposite amount. So those are Newton's laws. Now, that all looks a bit complicated, but often we can use the equation that says F equals ma. And this is a case where we've got a mass which is constant, and we've got an acceleration which is uniform. And effectively this says that A is equal to F over m. So the acceleration of an object depends upon the size of the force, A bigger force means there's a bigger acceleration, but equally if you've got a more massive object, so it's got more mass, but the size of the force is the same, then it's going to accelerate less. So F equals ma is a special case, but really we should be writing it out, or we should be defining it as the force being proportional to the rate of change of momentum. So in that case, what do we mean by momentum? So momentum is really this kind of quantity of movement, and the momentum of an object, which is small p, is equal to its mass multiplied by its velocity. And what's really important to consider is how linear momentum is conserved. And what we really mean then is that the momentum before is going to be equal to the momentum after. And what we're talking about after is we could talk about an event. So this could be an explosion, where initially things were both at rest and they move away in different directions, or we could talk about a collision where things come together and then they might kind of stick together, or they might move off again in different directions. So we're talking about explosions and collisions, both exciting things. So let's imagine we had object 1 and object 2. Object 1 has mass 1, object 2 has mass 2. Maybe that's going initially with u1 and this has got a velocity of u2. The momentum before is going to be equal to m1 u1 added to m2 u2. And again, we're just thinking about nice simple systems where we just have two objects. And again, you've got to remember that the velocity is a vector quantity, so it has direction, just like momentum, which is also a vector quantity. Now afterwards, these two objects, they might move off in the same direction, they might move off in different directions, they might stick together. Let's imagine we've got v1 and we've got v2. Well, that's the total momentum before, and provided linear momentum is conserved, which it always is, then we can say that's equal to m1 v1 plus m2 v2. This is not an AQA equation that you have to know, but this is a really useful thing of actually looking at how linear momentum is conserved in collisions and explosions. The other thing is that sometimes these collisions are elastic, and sometimes they are inelastic. So what does that mean? Well, basically, if we consider these types of collisions, if we think about the total momentum before and afterwards, the momentum is conserved in elastic and inelastic collisions, because that's always what happens, provided we're kind of just talking about this kind of closed system. If we look at the total energy involved, then the total energy is also conserved, because energy cannot be created or destroyed. What isn't conserved between those things is the kinetic energy. In an elastic collision, kinetic energy is conserved, but in an inelastic collision, kinetic energy is not conserved. And that means these two objects afterwards might have lower velocities, some of the energy has been dissipated, maybe gone out to the surroundings into the thermal store. So in elastic collisions, we don't conserve kinetic energy, but we do in elastic collisions. Now, something we can also do with this equation over here, looking at how the force is proportional to the rate of change of momentum, is we can rearrange it to say that the force multiplied by the change in time is equal to the change in momentum. And if we look at the force acting over a time on an object, this is what we call the impulse. And the impulse is going to be measured in Newton seconds, because we're looking at a force in newtons and a time in seconds. And over here we have our change in momentum, and again momentum's measured in kilogram meters per second. So sometimes in an ideal situation, if we were to draw the force acting on an object over a certain time, we'd get a graph that looks like this. So a constant force is being applied over a certain time interval. And if we were to actually look at the area underneath that graph, that area is going to be equal to the force times the change in time, which is therefore going to be equal to that change in momentum. But sometimes in real life, things aren't as simple. In reality, if you've got collisions between objects, perhaps a hockey stick hitting a hockey ball, the force will not stay the same and it will change as time goes on. Now, we can't just use the size of the maximum force, but what we need to do for this force time graph is still work out the area under that. We could be doing it by counting squares, which is horrible. You might approximate it using some triangles or a rectangle or something like that. Another point to note is that often the forces are quite big. So we've got kilonewtons and we've got very small time intervals of maybe milliseconds. So it's always worth just checking the axes on that graph. But effectively, if you know the area, and it's up to you how you work that out, we can then use that value to then look at the change in momentum of that object. And that's really important because we have certain things where the momentum is going to change by the same amount. But you might have a big force being applied for a small amount of time, but if we're going to change the momentum of an object by the same amount, we could also apply a smaller force for a much longer time period. And that's the idea behind things like crumple zones for cars, because the crumple zones increase the collision time. That means less force is experienced, and that means that we have safer devices. But talking of energy, let's talk about it a little bit more. So let's look at work, energy and power. Now, basically work and energy are kind of the same thing. Effectively, what we do is we do work, and that means that we transfer energy from one store to another. Now, effectively, if you've got an object and you apply a force to it over a certain distance, which is S over here, the bigger the force or the bigger the distance, the more work is done, and therefore the more energy is transferred. And we can say that W equals Fs. Now, this is the work done, and that's the force applied in the direction of the force. However, if the force was being applied at a different direction to that distance it's moved, it's a component of the force that we're interested in, and therefore we can say that Fs cos theta, where theta is the difference between the force being applied and the direction it moves, that actually then tells you the amount of work that's done. The other thing we need to know about is if you were to maybe look at a graph of how the force applied to an object depends on the distance that's moved. We don't always have the same force being applied for the whole distance, and so we might get a graph that maybe looks a bit like that. So maybe the force is increased as the distance increases, more like a real world scenario. And again, what we can then think about is the work done being equal to the area underneath that graph. So again, you can work that out maybe by dividing it to triangles, squares and rectangles to then work out the area under a force displacement graph to work out the actual work that's been done and therefore the energy transferred. How quickly that energy is transferred is also important. And we can then think about power. So power is equal to the rate at which work is done. So the amount of work divided by the time. Now, of course, here, the amount of work done is going to depend on the force times the distance. So we could also say for this one here that the power is equal to the change in force times the distance over the change in time, which we could and if that's a constant force being applied, that's going to equal to the change in displacement over time, and delta S over delta T is just the same as velocity. So another way we can write this equation is that the power transferred is equal to the force times the velocity. So that's another equation that you might see. Now, most of the time in real life, energy doesn't go exactly where we want it to. So we might be doing work on something, but not all the energy is transferred to the right place. And what we can then think about is efficiency. And the efficiency is really due to the ratio of what we get out compared to what we put in. Now, we might think about the energy, or we might think about the power, the amount of energy in and out per second. Now, efficiency, we can give it a number between 0 and 1. It's often more useful to think about as a percentage, so we just take this ratio, times it by 100, to get a value between 0 and 100%. So effectively what we're looking at is the amount that comes in to how much goes out. And effectively the bigger the amount of usefully outputted power compared to the total input power, the more efficient that device is. Not forgetting, of course, that energy is always conserved, and that means it can't be created or destroyed, just transferred between stores. And one of those stores could be mass, and later on you'll do a little bit more at looking at how E equals mc squared, how energy and mass are equivalent. But there are obviously two equations that you did do at GCSE. One of them looks at how the change in the gravitational potential energy is affected by the mass times the gravitational field strength times the change in height. And also we can look at the energy in the kinetic store being equal to a half mv squared. And there are lots of really nice examples where you maybe need to use energy considerations to solve problems. And it might just be thinking about maybe if you've got something like a simple pendulum, then that pendulum, at one point it's going to have maximum potential energy and zero kinetic, whereas at the bottom, just a fraction of a second later, its gravitational potential store will have been transferred to the kinetic store and then it's moving really quickly. So that's no more difficult really than GCSE, but you just get some more harder questions, as always with A-level. So that's a little bit about work and energy. And then the final part of this topic is looking at materials. Now the first thing is just a bit of a reminder that the density is the amount of mass per unit volume, measured in kilograms per cubic metre. And this thing is a material property, so it doesn't depend on the size of the object, it just is a material property that's dependent on the kind of thing it's made out of. We're going to come back to material properties in a sec. Something else we do, again, kind of what we've done at probably GCSE beforehand, is we're going to look at springs. And an experiment that you will have carried out is you look at how the extension of that spring, I'm going to call delta L because it's our change in length, varies with the force applied, often provided by a weight. And what you'll find is that initially we have a nice straight graph like this. And this is because as you keep applying more force to it, the length increases with this linear relationship. And that's provided, well, this is kind of Hooke's law. Now, this is up until we get to a point up here, which we call the elastic limit. Beyond that point, we then go into plastic deformation and things don't go back to the shape they were beforehand. Now, if we look at this linear region of the graph over here, we can see that the gradient is equal to the force divided by the change in length. And effectively, the gradient tells us about the behaviour of that spring. And this is what we call the stiffness, and that's measured in newtons per metre. And this stiffness has a symbol K, so we can write that the force is equal to K, the spring stiffness, times the change in length. And what you might do is you might even combine springs in parallel and series and see how maybe that affects the resultant stiffness of that system. So that's all about springs. The final thing about springs is that if we were to look at the area under that graph, that's equal to the energy stored by that spring. So the energy stored is going to be equal to 1/2 times F delta L. So this is, because it's a triangle, 1/2 times the force times the extension. So this is our elastic potential energy. Remembering, of course, we've already looked at things like kinetic energy and gravitational potential energy, and we can look at how this energy in this store could maybe be transferred to the kinetic or the potential stores. But that's looking at springs. Sometimes it's more useful to actually look at a material property, not like density, but maybe the material property of whatever that spring or maybe wire is actually made out of. And what we can then look at is stress and strain. And what we're interested in are when things are being pulled apart, and that's under tension. So what we can look at is tensile stress, and also we can look at tensile strain. Okay, strain and stress sound similar, but the stress is equal to the force per unit area, so F over A, whereas the tensile strain is equal to the change in length over the original length. And if we were to plot this data, maybe you're getting a long piece of copper that you're stretching some copper wire in the lab, is we can actually start to plot some data for stress and strain. And what we get then is maybe a graph that looks a bit like this. We can see it's kind of similar to this. Here we had force, this is force over area now. There we had change in length, now it's change in length over the original length. And then we get some data about the material properties for that metal. Now you'll see that at the start we have this linear region, just like we had with that spring there, and here we have something where we can look at the ratio of stress to strain, and this is what we call the Young modulus, and that's just the ratio of the stress to the strain. Remembering, of course, that we actually get quite big values for stress, small values for strain, and therefore things like the Young modulus might be in gigapascals, so really high values. We also get to a point when the material breaks. So over here we maybe have elastic behaviour when it goes back to the original shape. Up here we have plastic regions, and again we've maybe got the elastic limit at some point over here. We've got the limit of proportionality where suddenly we don't have this straight line anymore. And the ultimate highest value we get to over here, sometimes called the ultimate tensile stress, is what we call the breaking stress. And that's where that component or that material has actually fractured. Now, there are two main types of material. We get things that behave in a brittle way, When they're brittle, they might be quite tough. You might get quite high stress that it can withstand. But when it breaks, there's no plastic behaviour and it just snaps. So that's our brittle behaviour. Other times we might have something which behaves a bit more like this. And this is where we have something which has quite a lot of plastic deformation. And therefore these things, they keep bending, but they don't actually break for a long time. So they have quite a big strain. They can bend a lot before they actually finally fail. So material properties like brittle and plastic behaviour can also be seen on the graph like this. So hopefully something I've talked about in this video will help you as you're doing your revision for the AQA Mechanics and Materials module. Don't forget that you can subscribe to me on YouTube. You can also go to my website and sign up to get hundreds more videos, and there's new stuff being added all the time. So I really hope you've enjoyed the video. If you've liked the video, just press like, make sure you subscribe to me, and I'll see you again for some of the other modules. Thank you very much for watching.